Great. And can you see my screen in full screen?
Yes.
Great. Thank you.
Thanks.
Good afternoon and good morning, everyone. My name is Manolis Kargiantoulakis. I'm a senior data scientist with Diagnostic Cardiology. This is a general AI-ECG session, and we're starting with a presentation on some general basics in AI. I wanted to, avoid giving some academic or encyclopedic kind of definitions for things, and wanted to give more conceptual understanding on some very important concepts that would be helpful for actual people that are not experts in the space. So, artificial intelligence and machine learning, AI and ML, we could go into definitions, but for the most part, we can use these terms interchangeably. In any case, the outputs can easily appear as magic from revolutionary AI-ECG insights that have been shown in the literature, and you will hear about more later today, to much higher level objects like complex images and text and human language. It can easily appear as magic, but fundamentally, these new techniques, the advances with these new techniques arise from applying some very well-known optimization techniques, just at a new scale. So one definition that I will give to ask the question, what is machine learning? And these definitions go back all the way to the 50s or reformulated in the 90s. Fundamentally, a definition would refer to the ability of algorithms to learn directly from data, to improve some performance measure, and use that to make more accurate predictions for data that have not been seen yet. So this is a definition that is correct, but it could apply very widely. So even something as simple as, so this is my one math example. And I will keep it very shallow, and I promise it will be the last one. But even something as simple as a linear regression to get the best parameters for a line could fit that very general definition. So we have a set of data, and we want to fit for the parameters of a line. The parameters of a line are these A and B parameters that define a line. And we aim to learn the best A and B directly from the data. So this is a model for a line that allows us to predict Y for any new value of X. And this is a very simple example. We can do it even by hand on pen and paper, but fundamentally, we can do this by minimizing what we might call a loss function, which very simply can be the squares of the differences of the data from the prediction. And an optimization technique, if we wanted to do this computationally, could be gradient descent to find the best A and B parameters. I won't go too deep into describing this, just to say that these terms that you may have heard in the context of machine learning could very easily be applied in a much simpler problem, like what you see here. So what is really novel about modern machine learning? So again, if we have a set of data that I have generated here, and if we can very simply fit it with a line where we need to find the best parameters A and B, with a modern machine learning approach, we might do something like build a neural network that I have built here, let's say with 500 parameters. And now we can learn from the data and at any given point, predict the best value of Y for any given X. And these predictions I've plotted here in orange. And the point here is that we have traded our description of the data with just two parameters, A and B. And we went up to a function with 500 parameters. So obviously with that increase in scale and dimensions come the requirements that you're probably well aware of for much higher data and much higher computational requirements. But fundamentally, we are released from the modeling task. We no longer have to define the equation of a line to describe the data. And that allows us to capture very nonlinear effects. And in fact, because I have created the pseudodata here, I can tell you that a line equation is incomplete. There are more effects here that a neural network can capture nonlinear effects and describe it better, and in principle achieve better performance. So you may have heard the term AI can be a universal approximator. This is where this applies to. This is what it refers to. A neural network is basically an abstract function that can model anything, arguably. So even when the input information is very highly complex, we can still predict the output Y from an input X with much better performance before. And again, we are released from the very difficult, very constricting modeling task. There are trade-offs that come with that. With higher complexity, the abstract function loses interpretability and explainability. We don't have a clear image on how a neural network combines the information to give a prediction. And also just losing the information on the A and B parameters, even if they were an incomplete description of the system, they still captured a lot of very useful information and meaning that are very useful for human users that aim to understand the system that they describe. And they are sensitive to bias and errors in data. Data-driven optimization does not automatically confer common sense to a model. And it is very easy for a model to acquire biases. And that's where the need for external testing and validation for these models, this is kind of a new and very urgent need that goes hand in hand with these new capabilities. So here's another example from the AI-ECG literature. So here's a paper where the authors try to predict the non-cardiac surgery risk for outcomes for the patient for in-hospital myocardial infarction or mortality. And they built a deep neural network and machine learning systems to predict that. There's a benchmark that is currently in practice for this kind of risk. It's called Revised Cardiac Risk Index for preoperative risk, and you can find it on medical calculators. And as you can see, it's an expert-crafted model, and it scores from 0 to 6 for 6 risk markers based on clinical parameters like what is the kind of surgery and a lot on the history of the patient. So a current calculation for the risk that exists now in practice leverages these 6 parameters in a pretty straightforward manner. The authors in this paper show that they can improve performance on risk prediction just using the information from the ECG waveform, just reading in the ECG data. And they can do even better when they combine with the ECG waveform 43 clinical parameters, including the 6 that are included in the risk index currently in practice. So using AI and machine learning methods, we can optimally integrate all this kind of information. So we go from using not just these 6 risk markers used here, but 43 more. And we can read in the entire ECG waveform and combine that information optimally. So this kind of amount of information from all kinds of different sources can now be combined together in a way that was previously impossible. So of course, we should be able to get much better performance than was previously possible. We talked a little bit about the kind of inputs, whether it's a raw waveform or clinical markers. We refer to machine learning models or classical machine learning models like random forest and gradient boosting are 2 examples of these kind of models that operate on structured features. sorry, excuse me. So this could apply very, very generally on any kind of input, but for the ECG, these structured features could be the kind of clinical variables that we discussed in the previous slide. Or when we talk about the ECG waveform, this would be features of the ECG waveform that are expert crafted or from expert systems. So this could refer to wave durations and amplitudes or beat-to-beat measurements. So these are all the kind of structured features that go into classical machine learning models to optimize a classification task like ECG interpretation. And a very useful distinction between machine learning and deep learning, and you can find plenty of these distinctions, but one useful one is that deep learning systems, and we generally talk about deep neural networks here, can process the raw waveform, and they have no need for structured features at their input, but feature extraction is part of their architecture. It's something that is a little bit underappreciated about deep neural networks. Feature extraction is part of their operation. It's part of what they learn to do. And then they also learn to optimally classify and achieve optimal performance for what could be the same task. I'm not sure I can see questions. So Sophia, please let me know if one comes up.
No questions so far. So if you have any questions, don't hesitate to answer them.
Thank you. And here's a little bit more information and detail on the feature extraction part. This is specifically on the convolutional neural network architecture. This is perhaps the most common architecture in the AI-ECG literature, although by no means the only one. The transformer architecture is also very powerful. So for any kind of input, an application of a convolutional operation with various kind of features, various kind of filters, detects low-level features. And these features can be very basic, like detection of edges, like one object transitions to another object. It's like someone learning to see for the first time. And these operations are applied in what might be called convolutional blocks. These are standard combinations of layers that we don't have to go into detail now. And with successive application of these convolutional blocks over and over, low-level features are combined into mid-level features and then into higher-level features. And generally, if you can tell from this picture, the features as we move to the right are of higher complexity, although generally abstract and not interpretable. So this is again, the feature learning or feature extraction part of a neural network architecture. They create some features that they can then leverage, they can use and apply classification on those. And these classification layers are not that different from the kind of layers that are applied on the structured features that a human could understand more easily. So with that breakdown of a neural network operation into feature extraction, feature learning, and then optimal classification, we can understand foundation models like that. You may have heard the term foundation model before. It is used probably most commonly in large language models, but it can apply much more generally to any kind of data. It can be text or image or even ECG data. So by training and optimizing the feature extraction, the general purpose learning, we can create a foundation model that, for example, knows how to read an ECG and optimally break it down into structured features. Excuse me, not structured features, but higher level features that are embedded in the foundation model. And then, though, that kind of basic foundation model can be classified for any task-specific optimization or what might be called fine-tuning. So, for example, a foundation model that has learned to optimally read an ECG can then learn to optimally classify ECG interpretation or arrhythmia or specific endpoints for structural heart disease. And you might understand now why the term is so important for large language model applications, because those applications take so much data and training that doing that once makes a lot of sense. We have implied so far a lot about the kind of learning. We're mostly talking about supervised learning. Here are the models: train and learn from labeled examples for which the ground truth is known. So in the ECG space, the data is often very large databases with millions of ECG records, or it could be more specialized data sets depending on the kind of application. But in supervised learning, we need to know the ground truth about each record. So the classification task could be a wide classification for general ECG interpretation that could have something like 50 targets, or it could have just binary classification, whether it's a yes or no answer for an outcome or underlying classification or prediction. So for each record, we need to know what we might call the label associated with a specific ECG at the input. And you might foresee that there are issues with just binary classifying every record with yes or no, or there are issues with the ground truth being not precise in real world databases. And we need to optimize some performance metric as part of learning to optimize the model. And again, this comes from assessing the model predictions against the ground truth, against the set of labels. So there are various metrics that would describe how the model predicts. For example, this is a very simple picture for just binary classification. So we compare negative and positive model predictions against the ground truth. So a confusion matrix like this gives the whole picture of how good are both the positive and negative predictions of the model. But we need specific metrics to convey the model performance much more usefully. So accuracy, for example, is the metric that describes how often is the model correct in general, on average. Sensitivity is the fraction of true positive cases that the model can recall. Specificity is one that can be very easily be confusing for people because we're not used to thinking about how good we perform in true negative cases. And then the positive predictive value or precision is how often is the model correct when it gives a positive prediction. And that is a very, very important metric, I think, for clinical practice that is often underappreciated. And these metrics, to be interpreted, it requires understanding of the prevalence of the specific target and the population on which they are reported. So understanding these metrics can be very challenging very often. And the advice that I would give to people that are not experts in the space would be to ask the questions: just what is the sensitivity and the positive predictive value of the model for the population that you care about? If you have these two answers, then you understand probably the most you can about a model, and you avoid too many confusions. But getting the answer on the positive predictive value for the exact population that you're interested about can be very challenging very often. So as I said before, data-driven optimization comes with unprecedented potential for bias and overfitting. In some sense, the brute force optimization of deep neural networks, in a very real sense, aim to maximize as much bias as they can get away with. And some classic examples of that, and maybe a little extreme, is here a neural network learns to identify lesions as malignant just by seeing a ruler drawn next to it. That's an indication that it finds as the best shortcut to tell if the lesion is malignant, ignoring looking at the lesion itself. And another classic example refers to this a little apocryphal, refers to the US Army, apparently, for a task of detecting camouflage tanks. A neural network model can perform very well, but in reality, a bias in how the pictures were created is the answer to that, and the model does not generalize well. So these are examples, again, a little extreme examples, because these can be fixed pretty easily, but they demonstrate that data-driven optimization does not confer common sense. And there's a need for external validation and training on diverse datasets. So again, a little extreme examples, but these kind of fundamental dangers with machine learning optimization can arise in much more subtle and much more difficult to control ways. So controlling the scalability, accuracy, and generalizability across a range of scenarios is what will make or break these models. And different scenarios, different contexts is what we're talking about. Humans can easily transfer knowledge and understanding from one context to another. This is what machine learning optimization can be very weak at when it is presented with a new context. And that's why having very diverse training and validation data sets is very important. So there are revolutionary capabilities that are demonstrated in the AI-ECG literature, from reduced lead wearables, deep neural networks that use reduced leads to get as good performance as a 12 lead, for example, is a fantastic application for machine learning, if anything, because the ground truth is very solid. You just take a 12 lead and try to reproduce the same output from much reduced lead. You can do better than the 12 lead interpretation, but if that is all you're going for, then that is a fantastic application because of how good the target labels are. But we can also achieve improved ECG interpretation performance, detection of structural heart disease. These are endpoints that were previously completely inaccessible from automated ECG interpretation, and prediction of risk or outcomes for patients. So the ECG being ubiquitous, low cost, and simple, it is the perfect gateway to extract deeper insights and offer AI-enhanced decision support to clinicians and create new cardiac care pathways for patients. You have probably heard about the black box problem. So without specialized techniques, as we mentioned before, there is no explanation why a prediction for a deep neural network is given. And that can be problematic for integrating AI-ECG models in practice, especially in the clinical setting. Clinicians need to assess the outputs of an AI-ECG tool. It is difficult to build trust in the clinical community without an understanding of context and reasoning for the output of a tool. But in many cases, a black box that performs better is good enough. And absolutely, this is a paradigm that is the most straightforward way to bring these models to practice. It just means that it comes with a lot of trade-offs. It makes it more difficult for the clinicians to trust the model or to use the output for making clinical decisions. So it would be much better if we could design human-centered AI systems that, rather than displace human abilities, so a black box output that doesn't take into account fully how it could be used in the clinical setting, we would much rather have something that amplifies and augments the human and empowers human agency and judgment. And explainability of the AI model is a key component of that. It would allow the clinician, the human in the loop, to assess the output of the tool and use it optimally for their workflow.
Just a heads up, we're running out of time, Manolis. So 3
Thank
minutes left. Thanks.
Thank you. And yeah, I only have 2 slides. So explainability being so important, there has been a lot of progress working on the field of explainable AI. Salient CMAPS is one very advanced effort to visualize the regions of an ECG, for example, that are of importance for the output, the prediction of the deep neural network. And you see a couple of examples from the literature here, even for something as advanced as detecting hypertrophic cardiomyopathy or for detecting left bundle branch block. Highlighting the region of interest could be one way to look into what the deep neural network is seeing. And there are many more techniques that are researched. It's a very wide, very active field to provide context around the output of the AI-ECG. So again, this it's very important, and the significant focus on explainability research highlights how impactful and important for the success of these models for clinical implementation. And finally, you've heard about large language models. These can generate and interact in human language while processing large amounts of unstructured data. Large language models are basically applying all the concepts that we talked about in much larger scale, in very large scale of abstraction. They have been very successful as co-pilots or digital assistants. It's like having a PhD in every room, is how that is described, making expert information available to everyone, and integrating the entire information about a patient for real-time personalized decision support. So there's a huge potential and vision here for more efficient and integrated workflows. So that's it. Thank you for your attention. AI and machine learning methods, can leverage data-driven optimizations that were previously inaccessible. So there's huge potential to revolutionize healthcare and cardiology specifically, with the potential to empower clinicians and improve patient outcomes and make workflows more efficient. There's impressive research in the space. You will hear about much more about that in the next talk by Dr. Ram. And there are still barriers that remain. You don't have all these capabilities in your practice today, but there's significant progress achieved in the implementation science as well. And you will hear a little bit about that in the talk in the later. So thank you very much. And I hope we have some time for questions.
Thank you, Manolis. Yes, there's actually just one question in the Q&A, and maybe we can quickly actually postpone this one, because the question is, does Muse include AI machine learning? If yes, how does it work? And I think this question is something we can take as a final question after your next presentation, right?